All right, tonight we're extremely fortunate to have Ananthan Karunakaran joining us to give our feature presentation. Ananthan completed his PhD here at Queen's before moving on to a postdoctoral fellowship at the Institut de l'Industrie. And then after completing a postdoctoral fellowship there, is now an NSERC fellow at the University of Toronto. Ananthan studies some of the faintest galaxies in the universe and is particularly interested in trying to figure out how these things form and where they come from and what do they tell us about cosmology and the universe in general. Tonight, he's going to be telling us about becoming an astronomer for the comfort of your own home. And without further ado, I'll pass you on to him.
Great. Thank you very much. Okay, great. I had a count of how many people were here in person. I don't know how many people are here online, but we took our dog out for a walk this morning, and I felt like I was going to get blown into the lake from these gale force winds, which is an absurd event in and of itself. So thank you for very much for coming out in person. And the motivation for this talk today really stemmed from the fact that astronomy now has very much become a very data-driven endeavor. Folks have these very interesting telescopes at home as an enthusiast, but quote-unquote professional astronomers use unprecedented levels of detail from next generation facilities with telescopes that we couldn't even fathom having that are the same size of our homes, really. We couldn't have them in our backyards. They are the same sizes of our houses. And so what I wanted to try and sell you here today, for those of you that are here and for those of you that are online, is that we can do a lot of the science that we might be interested in from our backyard, from the comfort of our couches, which is something that I like. Maybe you like it as well, but maybe you like being in the backyard. So I don't want to deter you from doing that. So that is the motivation of this talk. So I also want you to be very comfortable in asking any questions throughout the entire sequence of the slides that I have today, with any sort of question that you have. So whether it's a mundane question about what a certain telescope is doing, or what one of the pictures in my slides really mean from an astrophysical perspective, I'm happy answering any questions that you might have. So the very first thing that I want to describe to you is what an enthusiast, someone that is working in their backyard with a small, relatively small telescope might be doing. So you might have something that a small little telescope or a telephoto lens that you connect to your digital SLR camera or DSLR or mirrorless camera, as some of you folks have, connect to a very detailed lens, or you have a very complex telescope, as I know some of you in the audience may have at home today. And these give you a very interesting perspective of the universe that you might not be able to really appreciate by looking at a very saturated sky from a relatively dense city. So these are the sorts of images that you might want to get. So you have something that you might get like a star cluster, like the Pleiades here, or a very interesting astrophotography perspective, like these trailing stars that you might be interested in. For those of you that might not want to invest in a mirrorless or a digital SLR camera, a single lens camera, or a very complex setup in your backyard, you can start to get images like this, maybe, which is an astrophysical campaign that has been put together using enthusiast level telescopes to study astronomical level features of known objects. So this is Messier 101 or NGC 4557, which is a nice spiral galaxy in the local volume. And folks have detected these very low surface brightness galaxies that are in these red squares and green squares in this figure. But you might be able to do this from your backyard, or you might be able to do this from your cell phone. So this is the C-Star S50, or the C-Star S50. This is not an ad for those of you that are online, those of you that are in person. I'm very astonished by some of the detail that you can get from a very small telescope. This is the size of a laptop. but it's connected to your phone via an app, and it can get you very detailed pictures of the Orion Nebula here on the left, or of M81 here on the right. It's amazing where things have come in the last, I don't know, 20 years of detailed research that has gone into how we can improve our astronomical instrumentation. And this technology that's used in this C-Star X50 is the same technology that's in your phone. So if you don't want to go and spend an extra $500 on this toy, more or less, you can also get a tripod and hook your Android phone or your iPhone up to this tripod and hopefully track an object that you're interested in as well as you can to try and get detailed observations of whatever you're interested in the sky. But if you want to follow a more quote-unquote traditional astronomy pathway, I just want to outline what this really is. And this is to become, again, a quote-unquote astronomer. So you might spend a few years in an undergraduate degree at some sort of a university in whatever country you may choose to do that in. You then may pursue a few years of a graduate degree towards a doctoral degree. And this is 3 to 4 years, maybe 5 years, depending on where you're doing this in the world. And in these 2 degrees, you will start to develop a lot of different skill sets that, again, I don't think are really sold to the public in the same way that they should be. You'll start to do a lot of math in your undergraduate degree and start to try and understand a lot of physics with that math in your undergraduate degree. And if you choose to jump towards a graduate degree, whether it's a master's or a PhD, what you'll start to realize is that the problems that you're solving from your undergraduate to your graduate degree are likely a lot simpler than some of the 3rd or 4th year problems that you're solving. The math is not necessarily as intense, it might be as intense, but it's not necessarily as intense as some of the hardest problems that you'll get on your final exam. So that's a bit of a relief for those of us that are pursuing a graduate degree. But what that does tell you is that if you want to leave and get a bunch of money, I didn't put that here, but if you want to leave and pursue a career that involves solving a lot of analytical problems, doing a consulting problem for a big telecom company that requires you to figure out what is this differential equation that you need to solve to figure out how we can optimize our performance so that we can minimize our costs. You can do that at one of these levels. Sure. But if you're interested in astronomy, you'll likely continue through this and pursue it for the science in and of itself. If you're interested in some sort of a topic, whether it's planetary science, whether it's galactic astronomy, whether it's extragalactic astronomy, so you're studying stars or you're studying stars beyond our Milky Way, you'll continue to do this beyond a graduate degree, so beyond a doctoral degree, and you'll start to do some postdoctoral fellowships, as I've done myself, as some of the folks in the audience have done or are doing themselves. And this is a few years of very detailed, very focused research, but it allows you to have the most efficient, most exploratory time of your career. And I think this is something that I've been told in my research career, but I think I'd like to share with you as well, is that this is probably the most privileged period of an astronomer's career because we don't have the dependence of a supervision. We're not teaching students, we're not teaching classes, and we get to pursue the most pure research career of our dreams. So this is what a lot of graduate students might be thinking of as a research career. And then we'll move on and we'll either become a professor of some sort, as Sarah is, and we'll get to teach students. And some of us really want to pursue that. That is something that is a goal of ours, to be able to provide the next generation of students with an idea of what is astronomy, what are we pursuing at a fundamental level, but an application at the forefront of the future. There are also some careers that are really interesting, particularly in the States or at national research institutes. So the Hertzberg Institute of Astronomy and Astrophysics in Canada is located in Victoria, BC. This is the foremost research institute in Canada that allows postdoctoral fellows to pursue a career as an astronomer. And this is really the only place that folks can continue a career to be an astronomer in. There are folks in the States that are able to pursue a tenure track of an astronomer, as a staff astronomer, as a staff scientist, but those sorts of careers aren't necessarily here, which is hopefully something that we can see in the future as we progress and as we build up our society here. But I just wanted to provide you with a bit of a pathway as to where folks are here. Does anybody have questions about where I've rambled on about here so far? No? Okay, great. I'll continue on. And there's a couple slides, maybe a little goofy, but this is the reality of it. So this is my brain, and I have an idea. I'll work through this idea myself a little bit, but then I'll talk to some of my colleagues, and we'll go back and forth. We'll go back and forth and back and forth and back and forth. I saw this galaxy. I think it's cool. I want to look at it with the Hubble Space Telescope for this reason. And my colleagues are like, hey, great job, great idea. I support you. Good proposal. Let's do it. We say, hey, Hubble Space Telescope, we want you to look at this thing. And there's a whole process for this. We write a proposal, we go through this whole process, and they're like, well, maybe you should do something like the Canada-France-Hawaii telescope, it's in Hawaii, before you come to us. So then I go ahead and say, hey, Canada-France-Hawaii telescope, will you look at this object for us? And they say, okay, that sounds like a great idea, Ananthan. You did a great job with the proposal. I think this is a good science project. And they give us this data. I go back to the Hubble Space Telescope. They say, hey, you did good work with the Canada-France-Hawaii telescope data. We'll give you this data with our telescope. This is great. We think it's going to be cool. And then they're like, hey, but you should also get this other data. This is a very large array. It's at a different wavelength. It's looking at different objects in this galaxy that you're interested in. But we think it's a good idea for you to also get this data. So we also go ahead and apply for time data. And it's a lot of work. This entire process might take anywhere from 1 to 3 years, depending on the availability of the facilities or the instruments on these telescopes. It's a bit of a crazy thing that we try to plan anywhere from 6 months to 3 years ahead of time. That's the trajectory of almost an entire master's degree or a PhD degree. So just to contextualize things for everybody here and online, most of us that are in a postdoctoral fellowship or further along are trying to plan anywhere from 6 months to 3 to 5 years ahead of time, solely so that we can get some Canada-France-Hawaii telescope, Hubble Space Telescope, or very large array time, just to study maybe one question that we're interested in. And it's a bit of a privileged position that we're in, but we're trying to push the limits of all of these facilities. And once we get beyond these facilities, we ask the government for more money so that we can build new facilities that can push the forefront of where we are using these facilities. And it's a lot of technological development and scientific data analysis development that goes into building these new facilities that really, hopefully, also helps society. And I want to make that clear as I go through that presentation. Now, say I get all this data. This is apparently me in this picture, but it's not. It's supposed to be representative. And then I start working. This is me. I'm going at it. I am on my laptop. I am crunching the numbers. I am trying to figure out what is going on with all of the data that I get from these telescopes. And then I'm angry. I don't know what my analysis is doing, my data collection is doing. It's very difficult to try and understand what's going on with all this data. So then I go back and I keep crunching these numbers and I'm trying to figure out what's going on. And it's a very difficult task trying to understand what's happening with this Canada France Hawaii telescope data, this HST, this Hubble data, or this VLA data, this very lightweight data. And I talk to my friends. I talk to my colleagues. I say, hey, I think I found something that's really cool, something that's really interesting. With all these data sets, I am breaking the forefront of astronomy. This is going to be in the front page of the New York Times. This is a huge, crazy data set. We're going to make something crazy here. This is a Nobel Prize in the making. So I start writing again. I am at it. I am writing a paper, a publication, so that everybody understands why this is important, not just to me, not just to astronomy, but to society as a whole. And I get this done. I get this published, and everybody says, great job, this is amazing. You win a Nobel Prize. This isn't necessarily the reality of astronomy. Not everybody gets a Nobel Prize. I'm sorry to burst that bubble for anybody that may be in the audience online or in person. But the rest of it is really true. We spend a lot of time trying to analyze this data, working through any sort of bugs that are in this open source network of codes and software, so that we can work with our colleagues, so that we can develop the best algorithms, the best sets of software, so that we can try and push this to any sort of public sector, but also so that we can apply this to our own astronomical data sets. And eventually, we may be happy and have a little publication that we put on our CV, and maybe that'll get us a little further along in our careers. But that's really where we're working to. We're trying to answer this question that we're interested in from an astronomical perspective, but the software that we work on, whether that's to analyze different data sets, to write this paper, or to write a new proposal, we're really trying to push the forefront of astronomy, but also society as a whole. What are the alternatives for folks that don't want to go through any of this? Some of you may be here in the audience, some of you may be at home. Some of you may be here that are listening to this online later on. If you don't want to go through any of this, you don't want to go through 10 years of school, a bunch of different postdocs, and then maybe a postdoctoral fellowship, and you just want to do some cool astronomy. I actually think that there's a bunch of different things that you can do that I apply in my own personal life beyond this. So I want to try and walk you through what are the alternatives. The very first thing is the Zooniverse and citizen science as a whole. So the Zooniverse is a platform that is very interesting from a STEM or a science or social science perspective as a whole. There are a variety of different projects that are available on this online platform. Again, you can Google this. This will definitely be your first search result on Google or whatever your search engine is of choice. But this will allow you to go through any sort of scientific or social science endeavor of your choice. This is an infographic that shows you how many people have volunteered on the Zooniverse platform as of 2024. So this is 2021 so far. So this is so far. We've had almost 2,300,000 people on the Zooniverse platform as of 2021. It's 3 years from now, or 3 years before. But a lot of different things have been done on this platform, is what I'm trying to say. There are almost 4.5 million gravitational wave glitches that have been searched through in Gravity Spot. And that's an astronomical endeavor that people have tried to understand from 2016 and 2017 with the LIGO and Virgo observatories, this is the foremost way to try and understand gravitational waves. And there have been 4 million people, or 4 million glitches that have been detected. It's kind of crazy that in, I guess, 3 years, that much has been done in this analysis until 2021. But this is something that folks here and online can get started with. And these are just the space-based things. So there are over 30, there's 31, so I said over 30 to seem more fancy. But it's really just 31. But there are some very cool science projects that are on here that I want to talk to you about very briefly. So the first one is Galaxy Zoo. I think this might be the most popular, I don't know if this is statistically the most popular, but I know that this is one of the most popular ways that folks have gotten into astronomy from a citizen science perspective. Galaxy Zoo started as a very simple way to classify the different types of objects that you've seen in just a simple JPEG picture. Does this look like a spiral galaxy, or does this look like an elliptical galaxy? And it really started out very simple. There are also some very interesting ones. So this one's called Blobs and Blurs, Extreme Galaxies and Clusters. I highlighted this one because I'm part of it. So this one, we are trying to study very extreme types of galaxies or stellar structures in the Virgo cluster of galaxies. It's very near to us. It's the most nearby cluster of galaxies, which is a very dense combination of all the galaxies that we have in a very nearby system. And we've actually, no, this is an update. Oh, I thought I updated this. We completed this. We're really excited that we went through over 50,000 now subjects that we've classified, and these are very extreme objects. And I want to show you just one of them that we published just this year. So this is Blue Cluster 6, but we colloquially call it BC6 or Blue Blob 6. It's this blue blob of points that you can see in these green ellipses shown in A, B, and C. And these are very interesting objects because nobody has seen them before, but they are isolated. They are not near another galaxy or another stellar object as a whole, but they have this huge tail of gas. And just for scale, we have a scale bar here. This is 50 kiloparsecs. And to give you an idea as to how big this is, 50 kiloparsecs, the Milky Way is just over half of this in size. So this entire structure, with just this small little blip at the tip of it, was detected in our signal, which is very cool. We think it's very cool. And we've completed the analysis from this citizen science project so that hopefully we can find more and more of these objects, and that hopefully society can be a part of the analysis that we're doing. Sorry? Yeah, so the Blobs and Blurs project was using the next generation Virgo cluster survey data, so it was optical data that was taken. And we use that in part with other optical data sets, as well as ultraviolet, so that we can see if there's any star formation going on. So these are very young objects, hence the blue blob side of it. And things that are bluer tend to be younger in their ages, but they also tend to emit in the ultraviolet. So we use not just the optical, but also ultraviolet as a double check or as a sanity check to make sure that the objects that we're seeing are with extra follow. Does that answer your question? Yeah, perfect. Okay, so I also mentioned gravity spy. So I also should have mentioned that there's gravity waves too, and I think there's one more. But gravitational waves are a very big topic over the last few years, especially with the Nobel Prize that's been associated with it. But Gravity Spy, along with Gravity Wave Zoo, These are ways that you can look through gravitational wave data so that you can analyze and see if there's any sort of a gravitational wave signature that you can detect in their data sets that they may not be able to get through with their analysis pipelines. There's also sunspot detective. So this is looking through archival data of sunspots on the sun. There's also solar jet hunter. And this is a pretty good segue, I hope, to another ad. So this is brought to you by the Queen's University Observatory Eclipse setup.
It's missing Kingston.
But it has Belleville for some reason.
But it had Belleville. So this is from
Why?
the Canada Space Agency.
Oh, why?
So Kingston is along here,
We get an extra minute over.
Yeah, anyway, I just wanna, this is an ad for the solar eclipse on April 8th, around 3 p.m. Make sure that you're at one of the spots that are posted on the Queen's University Observatory Eclipse 2024 website. So that you can make sure that you're at the right spot, you have the glasses that you need so that you aren't blinded by the sun on this day. So make sure that you tune in and you look forward to any sort of updates from the observatory here. Just a quick ad from our sponsor. Okay. Back to our content. Astronomy has a variety of subfields. I'm just going to take a quick drink of water. Okay. Astronomy has a variety of subfields, and I don't want to bore you with the details of cosmology or what is going on in the Milky Way. But I do want to tell you that there are a variety of different ways that you can go about studying a different subfield in astronomy. And when you're in your backyard, there's a very good likelihood that what you're looking at is something as a star that's near the sun or within the Milky Way. Sometimes you might go towards something that's a nearby galaxy, like I showed earlier. The C-star S50, again, not sponsored, not an ad. You might be able to see something just beyond our galaxy, like M81. But I do want to focus on how you can start to do some sort of near-field astronomy or extragalactic astronomy from the comfort of your own home. And this is, I think, the meat of the presentation. Before I do that, I do want to give you a bit of a science lesson. So sorry if you weren't expecting to get a science lesson today, but I do want to mention this is a bit of an extra. You're good. We're good. Okay, I'm gonna keep talking. This is Hubble's tuning fork, or Edwin Hubble's classification scheme as this figure portrays. But it's a tuning fork in that it is the shape of a tuning fork. But there are older elliptical galaxies, so they look more like a cigar or a bit more circular in their morphologies or their shapes. And as you go towards either side of the tuning fork, you see something that's a bit more like the Milky Way. It has spiral arms. It has much more star formation in this outer region than its inner region. And it has a bit of a more interesting shape, much more like this depiction of the Milky Way shown here on the right. And I wanted to give you that sort of a primer before I moved on to talk to you about some of the ways that you can start to do astronomy from home. That's not working. Okay. Okay, that's working now. Great. So I want to talk to you about two very interesting tools. And for those of you that have cell phones, if you want to pull out your cell phone and look up these two things, I am not going to judge you at all. So there's ESA Sky or ESA Sky. This is the European Space Agency Sky. So this is a tool that allows you to look at different astronomical data sets from a web browser. It's very powerful, it's very interesting, and it's the first thing that I'll start to talk to you about in detail. The second one is the legacysurvey.org/viewer. this is something that I think is a bit more at the forefront, and something that I use myself and some folks in the audience actually use themselves as well. And maybe online, I actually don't know who's online, maybe you know these tools already. But I want to talk to you briefly about both of these tools because they're very powerful and they allow you to do everything from your phone, from your laptop, from your desktop computer, whatever you want. So ESA Sky gives you this perspective at your first glance. So you see this beautiful galaxy. I've actually cheated a little bit and I've put in M33, which is the triangular galaxy. It's near our nearby neighbor Andromeda, which is M31. So you see this from a nice optical wavelength perspective. You can see that there are a lot of interesting red blobs in the foreground here. These are all Milky Way stars that we see in the foreground of this imaging data set. And this imaging data set is from the Sloan Digital Sky Survey data release 9. And it's shown as a color composite. And that's what's shown in the top center here, just a little bit left, top center. And we're seeing M33 from this perspective. Now we can change things a little bit if we hit this little layers menu in the top left of our directional menu here, select ultraviolet, and then Galax, which is the, oh, I don't remember the, geez, I should have memorized this off the top of my head. That's Galax All Sky Explorers. Galaxy All Sky Explorers. Thank you. I should have memorized that. But it gives you an ultraviolet perspective of the sky. It's a very wide field all sky survey that gives you a perspective from the ultraviolet, which is primarily used to study young stellar populations, so very new stars that are being formed within the last billion years or so. So if we look at M33 from this perspective in ultraviolet, we see that there's a lot of star formation that's going on in this object. It is shining bright blue to us right now. We can also shift to look at All-Wise, which is an infrared data set. But this provides us with a different perspective of galaxies as a whole. So we're looking at dust as a, again, from a global perspective, we're looking at dust from this perspective. And we can see interesting pockets of star formation in this data set because they're lighting up these regions of dust in this galaxy. So in M33, we can see regions of dust that are being lit up due to, if I can go back, due to this ultraviolet emission. They are then igniting some sort of emission in the dust particles that are then emitting at infrared wavelengths. So we have this multi-wavelength perspective solely by looking up M33, going through the layers in this very simple and very intuitive tool to try and understand the different properties of this individual galaxy. We can also right click. So if you, I don't know if you're on your phone, if anybody's on the phone or if anybody's online, you can right click on this object and then look through different astronomical catalogs that are available online. You may need to double click if you're on your phone in person or at home. And then you can look through something like Sinbad, the NASA Extragalactic Database, or NED, or Vizier. They have different tools that you can use to look through different astronomical data sets immediately. It's incredible how far we've come over the last 15 to 20 years in that we can connect to decades of analysis simply through a right click on a web page. I can't emphasize how crazy that is, even within the last 5 years, or I guess 8 years since I started at Cleans. Again, I just want to highlight that you can look through the layers here on the left one, you can randomize, you can look at what data is available. And then there are some very pretty pictures that might be available from the Hubble Space Telescope, the James Webb Space Telescope, and then I believe this is supposed to be the Nancy Gray Roman Telescope. Last bit, but I don't know if that's available yet. The next one that I want to talk to you about that is not necessarily correctly available here is the Legacy Survey Viewer. So if you go and Google, again, Legacy Survey Viewer, this should be the first thing that you see in your Google search. But what's not necessarily showing a very complete picture here is the MyLol 4-meter telescope that is in Arizona. It is taking some of the deepest and most detailed spectroscopic observations of our universe that I think we'll have for a very long time. It is part of the DESI, or the Dark Energy Spectroscopic Instrument Survey. It is going to tell us a lot about what dark matter and dark energy in particular is within the next, hopefully, 5 to 10 years, depending on how long the analysis takes. But what I want to focus on is what is in this weird bottom left part of the slide here. This is a very squished perspective of the entire night sky that's then projected onto an XY sort of flat plane. What you're seeing that's cut out here in this curved shape is the Milky Way plane that we're not able to observe in great detail. But everything else, we have very detailed, very deep observations of that we haven't been able to do before. So I want to tell you a little bit about the Galaxy Survey Viewer and how you can start to look at these things. Oh, before that, another spiel for the Dark Energy Spectroscopic Interferometer, or the DESI experiment. This is the distance in megaparsecs. So it's 1,000 times greater than the scale of the Milky Way that we're in, which is again 1,000,000 times the scale of, or 1,000 times the scale of where we are here today. But we have some very detailed observations. This is the foremost set of spectroscopic or redshift observations that we have of galaxies to date. This is the map that is the map that theorists will use to compare to date. And I'll leave it at that. If you have any questions, I'll be sure to answer that. Okay, so you get into the Legacy Survey Viewer and you see this beautiful galaxy and you click on it. This is what you're going to see. You're going to see link here, data, cut out, single exposures, look up in SIMDAB, discuss this object. We do have a social media filter for discuss this object. So if you see something when you're looking through the Legacy Survey Viewer, you can talk to other people about it if that's something that you're interested in. But what I want to tell you about is that you can share this with other people by linking here. It's a unique URL. You can also look at the data in and of itself. This is something that I think astronomers have been striving to push towards, to make all of the data that we're using in our analyses public. And having this in a browser, I think it's very cool. If you want this exact cutout, so what you're seeing in this image can be provided to you as a specific size in a single JPEG or an astronomical tool that we use, or astronomical data set that we use is called FITS. This allows you to have the entire data set in an unrestricted manner. From here, we can start to look at very cool things. So if I go back very quickly, you can scroll throughout this endless, and I mean endlessly. It's the entire sky. There will always be something that you're interested in. So maybe you saw this galaxy initially. This is NGC 5614, but just to the south of it, you see this little guy. You might right click on that or click on that and then open SIMBAD, which is an astronomical catalog that we have to see what other details that you can learn about this object. So you can start to scroll through the Legacy Survey Viewer in much more detail and look at different objects at a galaxy scale along the Hubble tuning fork that I mentioned earlier. So this object is quite a bit further along the tuning fork. It has a spiral structure, but you might see that something closer to the bottom left, closer to the right, is closer to the left of the Hubble tuning fork. It is earlier on the classification scheme that Edward Hubble put together. And I wanted to share a couple interesting objects that I found on the Legacy Survey Viewer. So at the center here, we have a nice spiral galaxy. I've blown up the contrast here that you're able to do in the bottom left here. But what you can see here, which I think is very interesting from an extragalactic astronomer point of view, is that there's a smaller galaxy that's interacting with this larger one. And if you trace back a little bit, follow my cursor here, you can see that this tail here is in fact likely associated with this interacting galaxy here. And this was, again, I did not search anything, I simply scrolled through the Legacy Survey Viewer and saw this object and thought it was very cool. And then went on to see that some folks have published some interesting work about these two interacting galaxies in detail, but nobody to date has studied this interacting tail that I'm highlighting with my cursor, that's shown to the south and to the left, or to the bottom, to the left, and to the right of this interacting object. Nobody has studied that part of this interaction to date. Another interesting one is something that's much closer to my heart, which is the dwarf galaxy. This is a nice, interesting one that you might see an interacting tail of close to this more massive galaxy here. So this is something that I simply found, again, scrolling through the Legacy Survey Viewer. It randomly places you at some NGC object, and you can start scrolling to your whim, whatever you want to do. And this is what I found. And nobody has found this yet. I'm working on analysis so that we can publish this for the first time, but I think that is kind of insane. We've studied the entire sky. People have looked into the sky for millennia, and this object is simply just out there in the sky for us to discover. One that we've published on is Tucana B, and this is very close to us. This is what it looks like in the Legacy Survey Viewer. We have some more detailed observations of it from the Magellan telescope, but you can see that there are some individual stars that we were able to detect with some deeper observations. So the Legacy Survey Viewer perspective is shown here on the left, and the deeper observation on the right. But this is our neighbor. This is right beside the Milky Way, and nobody had detected this until we started looking through the Legacy Survey Viewer. And this allows us to start to study the constraints of where galaxies came from in the first place, because it's so close to us, well, we had not detected it until, I guess, 2022, I should say. So it's very interesting to us that something so close by could be right under our noses. And then maybe for those of you that are interested, these are supergalactic coordinates in x along the x-axis here, y-axis here, z-axis here, and y-axis here. It's very much isolated, is what I would say. It is not near any other galaxy, so we can start to constrain a lot of different interesting reionization properties. And I can answer questions about that.
Great.
Yeah.
What is that thing with
Go back.
the thing to the left of the Tucana B? Is it
This little dwarfy
is
thing,
it part of Tucana?
it's not part of Tucana B. It is a low surface brightness object that's in the back.
So we know about it?
We do know about it. Well, we know. So, yeah, we do. Yeah, thanks for asking. But this is where think something like ChatGPT comes in. And this is an iffy topic for a lot of scientists, a lot of astronomers, a lot of people. I think ChatGPT, Google Gemini, Anthropic's Claude, whatever you want to use, maybe you want to use Grok from the folks at Twitter or X. But you can start to ask these sorts of questions, and I wanted to give you these prompts, and I can talk to you more about this if you're interested. Because people are building models solely based on these large language models or LLMs, like ChatGPT. You can start by saying you are an expert in the blank subfield of astronomy. I want to know blank. Can you tell me which telescopes are most frequently used to study blank? How can I access the data for blank? And can you describe the analysis and tools that are used for blank telescope? And I assure you, I wanted to record an entire example of this, but I didn't want to bore everybody. But these exact prompts can walk you through a very detailed analysis of anything from extragalactic to planetary astronomy. We have datasets that are available for galaxies or for planets, for stellar properties, or for galactic properties. Anything that you're interested in that has been crawled through the internet by one of Tech Hub's large language models is likely available for you to study. And I think that's what I think that I studied for. That's what I worked for, is so that the public can start to do these sorts of things, because I deal with more data than I think I can handle. So if the public wants to start working with that, then why not? And the take-home message that I want to leave you with is that astronomy is more accessible than you know. So whether that's working with a telescope in your backyard, working with Zooniverse or any of the citizen science projects, or starting to work with, I thought I had a picture here. I hope okay, anyway, I had a picture out here of a legacy reviewer and Pizza Sky. But using that or ChatGPT, Google Gemini, Claude, whatever you want, I think that it should be accessible to everybody, not just me, not just scientists. And I hope that I conveyed that to you today. I hope that I can answer any questions that you might have, whether that's in person or online. And thank you very much for listening to me ramble on for 30 to 40 minutes. Great. Thank you very much.